Okay, in this video, we're going to take a look at a couple of hyperbolic trig identities. And in doing that, that's going to explain for us why we call these functions that seem like they have nothing to do with trig and nothing to do with hyperbolas, why we call them hyperbolic trig functions. Okay. So the first identity is I want to take a look at the sum of cosh x plus sinh x. And I'm going to leave it to you to work out what that is. So that's going to be your task in a moment. Your second task is I want to take a look at the difference cosh squared x minus sinh squared x. And again, that's going to be a task for you to figure out what that's equal to. So what you're going to need to do is write these functions again in terms of e to the x and e to the negative x, so that then you can do the calculations. In this case, just adding, for this one, squaring and subtracting. So if you're watching this video, pause the video so that you can work these out. When we turn the video back on, I'll have the answers and I'll show the work for how I got those things. Okay, so we've got the answers up here. If I write cosh and sinh in terms of their definitions using e to the x and e to the negative x, I can see that I'm adding two fractions with a 2 in the denominator, so I get a 2 in the denominator. Here's an e to the x plus e to the x gives me 2e to the x. The e to the x and the minus e to the negative x cancel out. So I end up with just 2e to the x over 2, which is e to the x. So that's kind of neat. We can write e to the x, which has no symmetry whatsoever, as the sum of an even function, which is symmetric about the y-axis, and an odd function that's symmetric about the origin. Kind of a neat thing. Okay. The one we're going to use a little bit more is this second one. If we look at cosh squared minus sinh squared. Okay. So I wrote out cosh and sinh in terms of their definitions. Remember that when we're squaring things, we're multiplying together two copies of that thing. So we had to FOIL out the tops here. Now, e to the x times e to the x is going to give me e to the x squared, or e to the 2x. E to the x times e to the negative x, I can add those exponents. X plus negative x is just 0, and e to the 0 is 1. So the outside pieces give me a 1. The inside pieces also give me a 1. That gives me a 2. And then the last terms are e to the negative x squared, or e to the negative 2x, all over 4. We FOIL this out as well, same basic procedure. And then all I did is I rewrote the terms distributing that negative, because I'm going to be subtracting all three of these terms that are on top of that second fraction. And I can see when I do that, I get an e to the 2x and a minus e to the 2x, so those are going to cancel. I get an e to the negative 2x and a minus e to the negative 2x, and those are going to cancel. So all that's left on top is 2 plus 2, which is 4. 4 over 4. Whoops. 4 over 4 is 1. So we've got this hyperbolic trig identity that tells us that cosh squared minus sinh squared is 1. Now that should look really similar to our Pythagorean identity involving regular trig. So if we look over here, we know we have the relationship that cosine squared x plus sine squared x, or actually I'm going to switch from x's to thetas here. That's what I meant to do. If I call that angle theta, that's equal to 1. Okay. So that's our Pythagorean identity for regular trig functions. So if I set x equal to cosine theta and y equal to sine theta, then I can say, okay, so cosine squared, that's just x squared. Sine squared, that's just y squared equals 1. That's the equation for the unit circle. And so we can see that a point on the unit circle has its x value as cosine of some angle, where y is the sine of that same angle. And we say that the regular trig functions parameterize that unit circle. Now, if I try to do something similar with this identity, I've got cosh squared x. Let's go with theta. Cosh squared theta minus sinh squared theta is equal to 1. Now, if I try to do something similar and I say, let's let x equal cosh theta and y equals sinh theta, this becomes x squared minus y squared is equal to 1. Not the unit circle because of that subtraction sign, but when I'm subtracting squares like this is going to give me what we call the unit hyperbola. Now the unit hyperbola, if I were to graph this whole thing, would look like this. It would have a left branch and a right branch. That's the graph of this equation, x squared minus y squared is equal to 1. Need to be careful though, because cosh is never actually negative. So the points over here have negative x values. Those aren't going to coincide with any values of cosh, because we saw that cosh, when we graphed it, was always above the x-axis. But if I take just the right branch of this unit hyperbola, cosh and sinh parameterize just this half of the unit hyperbola. So every point on the right half of the unit hyperbola can be described as its x value being cosh of some number and its y value being sinh of that same number. And that's why we call these things the hyperbolic trig functions. There are other identities. I'm going to stop with these and just point out that if I wanted to get to some related identities, I could take this equation, if I divided through by cosh squared, notice this term would become cosh squared over cosh squared, which is 1. This would become sinh squared over cosh squared, which is tanh squared. And this would become 1 over cosh squared, which is sech squared. So just like with regular trig, you can get 3 different versions of the Pythagorean identity, you can get 3 different versions of this that involve ultimately all 6 of the hyperbolic trig functions. All right, and that's it for this video.